compact Kähler manifold. And I will prove that this polarization satisfies the properties that a polarized Hodge structures must satisfy. Okay, and that's essentially the Hodge index theorem. So I will prove, well, I will give a sketch of the proof of Hodge index theorem. And at the end, I will talk a little bit about intermediate Jacobians. Okay, so first of all, in order to get to the proof of Hodge index theorem, I will have to recall some definitions. So definition. So let X be a compact Kähler manifold. A K form, alpha is called primitive if the Lefschetz operator applied n minus k plus 1 times vanish on alpha. Okay, so this is the definition. I mean, when you restrict yourself to harmonic forms, you will get like the dual definition of a primitive homology class, but now in the Rham cohomology. So we denote like this the space of primitive the Rham cohomology classes. Prim is, by definition, the kernel of the Lefschetz operator from the harmonic forms to n and this looking at it via the isomorphism of the harmonic forms with the Rham cohomology. Okay, is this subspace. Right. So yeah, and the remark is that under this point carré de Rham isomorphism, the primitive part corresponds with the primitive part of this. Well, this definition is for k less or equal than n. Okay. I mean, we have to do. I mean, we'll just use it now for k less or equal than n. Okay. Okay. So proposition. Again, let X be a compact Kähler manifold. And alpha in PQ primitive form, primitive PQ form. Okay. Then we have the following relation. So we can compute the star of alpha, and it will be equal to the following thing: -1 to the k times k plus 1 over 2, I to the q minus p over n minus k factorial, the Lefschetz operator to the n minus k that applied to alpha bar. Okay, so we have this relation. In the case when you try to compute the star operator for a primitive PQ form. Well, this this proposition I won't prove it. I mean, it's quite long again, and since you know these operators are just defined in terms of the metric, of the value of the metric at the point, you can assume that you're in Cn with the constant metric, the standard constant metric in Cn. Right, so the proof is like prove it for Cn and this Hij equal to the identity. Right? Well, I won't do it, and it's long. I mean, you can read it. It's not that easy. But I will skip this part because, well, I don't want to do it. Okay. So now definition. Okay, let X be a compact Kähler manifold. Of dimension n. With associated 1-1 form omega. Okay, so for every k, less or equal than n, we define the polarization. Polarization on the real the Rham cohomology group, and we are identifying this with the intersection of well, no, this is just, I mean, this is the space of the Rham cohomology classes that are invariant under the complex conjugation. Okay. So we define it as Q. So it will be a bilinear map, alpha and beta, defined to be the integral over X, alpha wedge beta wedge omega to the n minus k. Okay, it's a bilinear form. It has an alternating sign here depending on k. Well, and this polarization satisfies a lot of properties that we will prove in this class. Okay. And we define their medium form on HK the Rham of X as, so HK of alpha and beta is by definition I to the k integral over X alpha wedge beta bar wedge omega to the n minus k. Okay, this is a Hermitian form. That's easy to check. And And we will use this Hermitian form in order to prove the properties of this polarization. Okay, so a remark here is that, well, I proved this Hard-Lefschetz theorem in the Rham cohomology, right? I did the proof, I don't know, maybe 2 class, I don't know if it was the last class, maybe, I don't remember. The thing is that using this Hard-Lefschetz theorem, we can prove the Lefschetz decomposition. And in cohomology, the Lefschetz decomposition is as follows. R less or equal than N R H K K K minus 2R. Right, this is the corresponding version of Lefschetz decomposition in the Rham cohomology. So now we'll prove. Now we will see how this metric, this HK, behaves with respect to this Lefschetz decomposition, and then we will check how it behaves with respect to the Hodge decomposition on each piece of the Lefschetz decomposition. Okay, so the first proposition. So the Lefschetz decomposition is orthogonal with respect to HK. Okay, and furthermore, HK induces the metric minus 1 to the R, HK minus 2R on every subspace LR H K minus 2R the Rham of X prime. Okay. Proof. And this is very simple. So let alpha equal to LR of alpha prime, beta equal to LS of beta prime for some R less than N's. And we have to check that these guys are orthogonal on it in each HK, right? So this HK of alpha and beta is what? It's I to the k integral over x of alpha wedge beta wedge omega beta bar omega to the n minus k, and this is I to k integral over x of alpha prime, which beta prime bar, which omega to the n minus k plus r plus s, right? And this is just I to the k integral over x of the Lefschetz operator to the n minus k plus r plus s applied to alpha prime, which to beta prime bar, right? And since we know these guys are primitive, so since alpha is primitive, I mean alpha prime is primitive, right? We know that this L to the n minus k plus 2r plus 1 applied to alpha prime is 0, right? This is the definition. And this guy n minus k plus 2r plus 1 is less or equal than k n minus k plus r plus s, and so this guy is 0, and so this is 0. Okay? Is this clear? Yes. Clear? Yes. Okay, and if r is equal to s, we have that this hk of alpha and beta will be equal to I to the k integral over x of L to the n minus k plus 2r. Well, it will be alpha prime, which beta prime bar, which omega to the n minus k plus 2r, and this is just minus 1 to the r, I to the k minus 2r, the integral over x, alpha prime, beta prime, n minus k plus 2r, and this is just minus 1 to the r, h k minus 2r of alpha prime, beta prime. Okay. So now we will prove the main theorem. Using this. So theorem. Let X be a compact Kähler manifold of dimension n, and let so then so the Hodge decomposition is orthogonal with respect to HK. Okay, and the form minus 1 to the k times k plus 1 over 2 times I to the p minus q minus k hk is positive definite. On HPQ of X prime. The primitive part of the PQ cohomology group, and this is just the PQ cohomology group intersected with the K, the Rham cohomology group, the primitive part of this. Okay, everything clear? Good. So proof, again, very simple. So let alpha PQ, let's say beta P prime Q prime, in HK the Rham of X. It is in the PQ cohomology and the P prime Q prime cohomology, and we're assuming that PQ is different from P prime Q prime. Okay, so we have to show that the HK of alpha PQ and beta PQ P prime Q prime is 0. Okay, and that's easy because HK of alpha PQ beta P prime Q prime is I, the integral over X of alpha PQ, which beta P prime Q prime bar, which omega to the n minus k. And again, this will be an n minus k form. This will be, so I mean, all this thing will be n minus k plus p plus q prime, n minus k plus q plus p prime, right? Is this correct? Right. So since I mean we know that p plus q is equal to k and p prime plus q prime is equal to k, one of these two sides is bigger than n, right? So this will be, the form will be 0, right? Okay, and for the second part, we have to use this proposition that I stated before. For the second part, note that, I mean, so HK of alpha for a PQ form, right? For a primitive PQ form alpha, we will have that HK of alpha is equal to I integral over X alpha, which alpha bar, which omega to the n minus k, right? And this will be equal to I to the k integral over X of alpha, which the Lefschetz operator to the n minus k applied to alpha bar. And we already compute this, well, we know how to compute this guy. So this will be equal to minus 1 to the k times k plus 1 over 2 I to the k plus q minus p n minus k factorial, the integral over X of alpha, which the star of alpha. And this is, by definition, the norm of alpha squared. Right, and so this is positive. I mean, this part is positive. And so we, in conclusion, we get that minus 1 to the k times k plus 1 over 2 I to the p minus q minus k, right? Hk is positive definite, right? Okay, so this theorem implies the Hodge index theorem. So Hodge index theorem is the following theorem. Let X be compact Kähler manifold of dimension n, and then the signature of the polarization of Q is equal to the following number. You sum over all A and B equal from 0 up to infinity, right? I mean, almost all of these things will be 0. The complex dimension of HAB of X. Okay, this is the signature of the polarization. This is Hodge index theorem. Proof. So, I mean, the signature of Q will be equal to the signature of the Hermitian form of I to the k h k. Right? And so it's enough to compute the signature of this form, right? And in order to do that, we just use both the compositions. I mean, we have by Lefschetz and Hodge the decomposition. That the kth the Rham cohomology group is equal to the sum for 2r less or equal than k of the Lefschetz operator r times. Well, here I have another sum. So it will be, let's say, a plus b equal to k minus 2r lr of h ab of x prime. Right? This is Lefschetz decomposition and Hodge decomposition. And so in order to compute the signature, it's enough to determine the sign of this form I to the k hk on each piece, on each of these pieces in this decomposition. Okay, so we already know. So we know that HK. So H. Sorry. This is the signature of Q, but for K equal to N. I mean, Q, the polarization, the signature of Q on this group, on the N, the Rham cohomology group. Right? So we have a Q for every K. I am saying that I can compute the signature for K equal to N. Okay? So it will be this will be N, this disappears. And we have this decomposition. Sorry, content N minus 2R. Okay, like this. So we know that Hn restricted to Lr of Hn minus 2R, the Rham of X prime, corresponds to minus 1 to the R Hn minus 2R. Okay, and each of these Hn minus 2R, when we restrict it to the AB cohomology group, we have that is the following thing is positive. I mean, minus 1 to the N minus 2R times N minus 2R plus 1 over 2 I to A minus B minus N minus 2R H N minus 2R is positive. This is what we already proved. And so we have to compute this. So this implies that so if we compute this number, it will be just minus 1 to N over 2 minus R. I mean, yeah, something that I forgot to mention is this is a compact Kähler manifold of even dimension N. Okay. So this Q will be symmetric. So this Q is symmetric. Right. So we'll get this number times I to the A minus B minus N. This I to the 2R will be minus 1 to R, so I can erase this. And I can write this guy, well, I can write it as S, as I to the N, right? So it will be like this, I to the N, Hn. This thing, right, is this correct? Yeah, I mean, it will be. The thing is equal to I to 2 times A minus 2N, right? IHN, and this is positive. And this is just minus 1 to the A IHN. by I to the n. Right, so we know that the sign of this form is exactly -1 to the a on each HAB prime part of this decomposition. And so we can compute its signature. So then the signature of Q, it's equal to the signature of I to the n Hn. It will be equal to the sum of A plus B equal to n minus 2r for 2r less or equal than n of -1 to the a h ab, right, where this HAB prime, where this HAB prime is just the complex dimension of HAB prime. Right? And so again, now we know by Lefschetz decomposition, we have that this HAB of x will be equal to HAB prime plus L to the r of HA minus R B minus R of x prime for all 2r less or equal than a plus b and bigger than 0, right? And so we can write. So we have that HAB of x is equal to HAB prime plus L times H A minus 1 B minus 1. And since by Lefschetz theorem, since L is injective on this space, we get that HAB prime is equal to HAB minus HA minus 1 B minus 1, right? And so the signature will be equal to the following sum. So then the signature of Q will be equal to the sum for all A plus B equal n minus 2r for 2r less or equal than n minus 1 to the A HAB minus HA minus 1 B minus 1. So this will be equal to the sum A plus B equal n minus 2r 2r less or equal than n minus 1 to the A HAB plus the sum. So now we will have here A minus 1 plus B minus 1 equal to n minus 2r plus 2. Again, this 2r less or equal than n. Here we have minus 1 to the A minus 1, HA minus 1, B minus 1. Right? Okay, and we can relabel this sum. So if we relabel this sum with A and B, we can write it like this. Right? And so what's the one that is missing? I mean, this sum will be equal to this sum, except in the case a plus b equal to n minus 2r. I mean, right? For every r less or equal than, for every 2r less or equal than n, the one that we are not having here repeated is the a plus b equal to n minus 2r. Right? So by third duality, by third duality, we will have that this signature will be equal to the sum of all a plus b congruent to n. I mean, n is even, right? So congruent to 0 mod 2 minus 1 to the a h a b. Right? So I mean, I'm using the duality on this second part, right? In order to attain the values where 2r is bigger than n, right? So this will be equal to by third duality. Okay, so the only thing that we have to check now is that it is left to prove that the same sum but with a plus b odd is 0, right? And this is not that hard. So why is this true? This is true because so by Hodge symmetry, we have that this sum a plus b odd minus 1 to the a h a b is equal to the sum a plus b odd minus 1 to the a h bi, and if we relabel this, it will be the sum of a plus b odd of minus 1 to the b h a b, right? So if we add them, these two things, we will get 0, right? I mean, this is equal to minus 1 to the a plus 1. And so this is 0. Okay? So this is the Hodge index theorem. It's is it clear? Yes? Okay, so a corollary of this, that sometimes it's also called the Hodge index theorem, is the following. So let X be a smooth projective variety of even dimension n, And let Y be a smooth hyperplane section and Z be n over two-dimensional algebraic cycle such that Y times Z is 0, but and Z is not numerically 0. This means that there exists some Z prime that it's also of dimension n over 2. I mean, let's say here in Hn x R alg such that it's also primitive, and Z times Z prime is non-zero. Then we know what's the sign of the self-intersection of Z. Minus 1 to the n over 2, Z times Z is positive. So in particular, if we're in the case of surfaces, on a surface, we're saying that a divisor that is not intersecting a fixed very ample divisor, and it's not numerically 0, then it has self-intersection negative, right? Sometimes this is called the Hodge index theorem. Okay, and the proof is trivial. So we know that Z PD, it's in the primitive de Rham cohomology is non-zero. This is the first. I mean, this is that Z is not numerically 0. And since it's algebraic, we know that it's a Hodge cycle, right? So this ZPD lies in the middle part of the Hodge decomposition. Right? And so since this number, minus 1 to the n over 2 C times Z, it's equal to minus 1 to the n over 2 of the integral over x of the Poincare dual of this, which itself, right? And this is minus 1 to the n over 2 of the form, right? Q applied to these guys, and we already know what's the sign of this. I mean, this will be positive. So everything is clear, right? Okay, what time is it? Okay, so now I will talk a little bit about the intermediate Jacobians, and this will be the last part of this L2 Hodge theory part of the course. So first of all, definition. Let X be compact Kähler manifold of dimension n. Then for every k equal to 0 up to 2n, we define define the Hodge filtration on HK by as the following filtration. So we have here HK the Rham of X. Now we remove the first part of the Hodge decomposition. So we have H1 K minus 1 of X plus H2 K minus 2 of X and so on. HK 0. And we continue in this way. So at the level P, we will have HP K minus P of X plus and up to HK 0. And we will continue until only the HK 0 part, and then we will have 0. Okay? So this is the Hodge filtration. The notation is like this. So we denote by this F0 of HK the Rham of X. This is contained on the F1. And you continue like this, FP. And this will be FK. Well, and this is FK plus 1. Okay, so this is the Hodge filtration. So note that from the Hodge filtration we can recover the Hodge decomposition. So since Fp of Hk the Rham of X intersected with Fq of Hk the Rham of X bar is equal to Hpq, we can recover the Hodge decomposition from the Hodge filtration. Right, and also we can define the Hodge cycles, I mean the Hodge classes. Hodge 2k of xq, it's equal to the filtration at level k of h2k the Rham of X intersected with h2k of X with coefficients in the rational numbers, right? Because, well, we know that the Hodge classes are real classes, so they are invariant under the complex conjugation. So it will be equal to the intersection of this with the intersection of the conjugated, and it will be hkk, right? Okay, everything, all these things seems like very trivial and useless, but they will be very important later. Okay. When we do this more algebraic part, we will work with the Rham cohomology, but defined algebraically, the algebraic de Rham cohomology. And in the algebraic de Rham cohomology, you will not have anymore this Hodge decomposition. You will just have the Hodge filtration. Okay, so now definition. Again, X compact Kähler of dimension n. So we define the we will define the intermediate Jacobian. So consider the map phi from h to n minus 2k plus 1 of x with integer coefficients to h to n minus 2k plus 1 with complex coefficients, and then consider this isomorphism, the Poincare dual, to, the Poincare de Rham duality, h2k minus 1 the Rham of x. Right, consider phi being this composition. Then we define the kth intermediate Jacobian j to the 2k minus 1 of x to be the following quotient, the 2k minus 1 the Rham cohomology group, mod the filtration up to level k plus the image of phi. Right, okay, so note that phi decomposes as the following map, right? It goes from h to n minus 2k plus 1 of x with integer coefficients, then to n minus 2k plus 1 x with complex coefficients, and then you have an isomorphism with h to n minus 2k plus 1 the Rham of x dual, and you have another isomorphism with h to k minus 1 the Rham of x, right? And so in particular, and what's, so let's call this, I don't know, psi. So under psi, we have the following isomorphism. So we have that psi sends the filtration of level n minus k plus 1 of h to n minus 2k plus 1 the Rham of x dual. It goes to what? It will go to this part, like h0 k of x plus h1 k minus 1 of x. It's not k, it's 2k minus 1, 2k minus 2, until hk minus 1 k of x. Right? I mean, this filtration starts from n minus k plus 1. So this is h n minus k plus 1 n minus k of x. And the dual of this will be this guy, the k minus 1 k group. And you go further, and the duals will be here, right? So we have this isomorphism, and this is exactly this quotient. This is the 2k minus 1 the Rham cohomology group mod the fk of h2k minus 1, right? And so this intermediate Jacobian can be seen inside this space, this vector space, right? So the intermediate Jacobian j to the 2k minus 1 of x is isomorphic to f to the n minus k plus 1 h 2k to n minus 2k plus 1 the run of x dual mod mod some lambda, I mean mod the image of h 2n minus 2k plus 1 of x with integer coefficients inside this thing. Right, where this map where I don't know, phi of delta, when we apply it to some omega form here, it will be the integration map for every omega in fn minus k plus 1 of h 2n minus 2k plus 1 the run of x. Right? And for every delta. Right? Is this clear? Okay, so these intermediate Jacobians are in fact complex tori, and so we will prove this proposition. Intermediate Jacobians are complex tori. And when x is projective, the first intermediate Jacobian, the J1, is an Abelian variety. This means that it's projective. So in particular, this proposition proves that for every Riemann surface, the Jacobian of the curve is an Abelian variety. You can embed it inside some projective space. Okay, so the proof, what time is it? Okay, so still have time. So the first part, we have to check that this subspace is a lattice, right? We already know that it is a finally generated Abelian group, right? So the only thing that we have to check is that this image, the rank of this image is the dimension of this space as the real dimension, right? So let lambda be this guy, the image of phi. We have to check that the rank of lambda is equal to the real dimension of this fn minus k plus 1 h 2n minus 2k plus 1 the Rham of x, right? And this is 2 times the dimension of it, but this is the half of the Hodge decomposition of this group, right? So this real dimension will be exactly the complex dimension of this group, right? And this is exactly the rank of the homology. So this is what we have to check, that the rank of lambda is equal to the rank of the homology group here, right? So the thing that we have to check is that whenever we apply phi, the rank of this module doesn't decrease, right? So it is enough to check that the kernel of this phi is the torsion part of this guy. Right, and this is quite simple. Just note that if some delta is in the kernel of phi, then the integral of delta of omega over delta is equal to 0 for every omega in fn minus k plus 1 of h2n minus 2k plus 1 the Rham of x, right? And when if we conjugate this, we will get that the integral of delta over, let's say, omega bar is equal to 0 for every omega bar in the conjugate of this group. And since the sum of these two guys is everything, we conclude that so then this integral is 0 for every omega in h2n minus 2k plus 1 the Rham is equal to the fn minus k plus 1, h2n minus 2k plus 1, plus its bar. And so delta must be in the torsion part, right? Okay, so this proves that the intermediate Jacobians are in fact complex toroid, right? But in general, they are not projective. They are not Abelian varied. But in the case where X is projective, the first Jacobian is an Abelian varied. Okay, so for the second assertion. So we know that this J1 of X is equal to what? It's equal to H10 of X mod some lattice that it's the image of H2n minus 1 of X with integer coefficients inside here by this PD, well, yeah, in H1 the Rham of X, and then we project it in H10 of X. right? And so how do we prove that this tori is in fact projective? What we have to do is to define a Hermitian metric here that is Kähler, and it's integral, right? I mean, the 1-1 form associated is integral. That's what we have to prove. So what will be the Hermitian form? So since we know that this is a complex tori, we can define it as a constant Hermitian form on this vector space, and it will define a Hermitian form on the quotient, right, on the tori. So we just need to define a Hermitian form here, and we already did that. I mean, a positive Hermitian form. So let us consider the form H1 of alpha beta equal to I integral over x alpha wedge beta bar wedge omega to the n minus 1 for every alpha and beta in H10. Okay, and H10 is equal to H10 prime. Okay. So we already know that this form is Hermitian and it's positive. This is Hermitian, positive definite. Right? And it's constant, right? So since it is constant on this vector space, when you induce the metric on the quotient on the tori, it will also be a Kähler metric, right? Because the 1-1 form will be also constant, right? So its differential obviously will be 0, right? So the only thing that we have to check is that the associated 1-1 form is rational. So let eta of alpha beta so we have to check that what will be omega. I mean, the omega associated to the Hermitian metric will be minus the imaginary part of the metric, right? And so we will just need to check that minus the real part of this is rational when we apply it to the elements of the lattice, right? I mean, so let this, the real part, alpha wedge beta bar wedge omega to the n minus 1. Right, so this will be minus the associated 1-1 form. So we want to check that this guy is rational, right? So we want to prove that this is Hodge, right? I mean, it's this is what we want to check, right? And how do we check that? To check that is the same as proving that the integral of eta over any delta belongs to Q for every delta in H2 of x with integer coefficients, right? This is enough in order to prove that this is a rational class, right? That's the definition. And so since we know that J1 is a complex tori, so since J1 is a tori, it's a torus, we know that the H2 is generated by the products of 1 cycles in this torus, right? I mean, you decompose the torus as products of circles, and the product of two of these circles will generate the whole H2, right? So it's enough to show that this thing, the integral of delta 1 times delta 2 of eta belongs to Q for every delta 1 and delta 2 in the first homology group of the Jacobian. Right? But the first homology group is the fundamental group of the tori, and it's the lattice, is the image of this phi, is lambda, right? So this is equal to under the identification, H1 of the Jacobian with integer coefficients. Let's say this is f of the image of H2n minus 1 of x with integer coefficients inside, let's say, H2n minus 1 of x with complex coefficients, and then the Poincare de Rham, H1 the Rham of x, and then the projection to the 1, 0 part. So under this identification, we know that delta 1 and delta 2 belong to H10 of x, right? So f of delta 1 and f of delta 2 belong to H10 of x, right? That it's the universal covering of the first intermediate Jacobian, and it's also its tangent space, right? So since we know that this, well, it's an easy exercise. To check that this integral over delta 1 times delta 2 of the 1, form will be equal to the form, but now as a bilinear map applied to f of delta 1 and f of delta 2. I mean, this is something that you can prove is simple, very simple. It's just a fundamental theorem of calculus. So what we have to check is that this thing belongs to Q. For every delta 1 and delta 2 in the first homology group of the intermediate Jacobian. And this is almost tautological. Well, it's not that. So so we already know that this f of delta 1 and f of delta 2, they are 1, 0 forms. So this is alpha 1, 0, and the f of delta 2 is some beta 1, 0. But they appear as projections of something, right? So there exists a alpha 1, 0 plus alpha, alpha 0, 1 plus alpha 1, 0 equal to some mu 1 PD, right? For some mu 1 in H2n minus 1 of x with integer coefficients, right? And the same thing happening for beta 1, 0, right? Some mu 2 PD for some mu 2 here also. Right? This is the definition of being in the image of that map, right? And so since these two cycles are integral, I mean they are real. The PD of them is real. So in particular, we have that this alpha 1, 0 is equal to the alpha 0, 1 bar, and the beta 1, 0 is beta 0, 1 bar, right? And so what's the value of this bilinear form applied to this? So so eta of f of delta 1, f of delta 2 is equal to what? It is equal to the real part of the integral over x of alpha 1, 0, wedge beta 1, 0 bar, wedge omega to the n minus 1, right? And this is equal to 1/2, right, of this thing, the integral over x of alpha 1, 0, wedge beta 0, 1, wedge omega n minus 1, plus the conjugated of this thing. And the conjugated is alpha 0, 1, wedge beta 1, 0, wedge omega to the n minus 1, right? And this sum is equal to 1/2 of the integral over x of the mu1 PD, wedge the mu2 PD, wedge omega to the n minus 1, right? And since we know that x is a Kähler manifold, that it's projective, we know that this omega is a rational class. I mean, it's an integral class, right? And also mu1 and mu2, they are integral classes. So this whole top form will be also rational, right? And so this integral will be rational. I mean, you can see this as 1/2 of the intersection product of mu1 times mu2 times, let's say, y to the n minus 1, where this y is the hyperplane section. And so obviously, since all these things are defined over the integers, this will be in the integers over 2. So this will be in Q. Right? And that's the proof. Okay? Is it clear? Well, kind of believable? Okay, do you have questions? So next class, we will change the topic, and we will talk, I think that maybe a little bit about the homological algebra, and then we will continue with chief cohomology and hypercohomology and so on.